Hi, I'm Michael Thomas Wheel-Adkins, and what you're about to hear is the foundation of something I call the Temporal Strand Theory, a new way of looking at the universe that starts with time, not space. Let me explain what I mean. For more than 100 years, physics has treated space as the stage where everything happens. The focus has been on where things are, how far apart they are, and how they move throughout space. Time, on the other hand, has mostly been treated like a stopwatch, something that just ticks along in the background while the real action plays out in space. Einstein did shift that a bit with his idea of spacetime, combining time and space into one four-dimensional framework. That was groundbreaking. But even then, time was just one axis on a larger grid. It still wasn't doing anything by itself. It was passive, it was a label, not a cause. And in quantum mechanics, time is even less involved. It's not part of the wave function. It's not something you can observe or measure within the system. It doesn't entangle, it doesn't collapse. It just sits there as an outside parameter, ticking forward, untouched by the rest of math. That always felt wrong to me. So here's the shift I'm making. What if time isn't just a background? What if it's not just a label we use to keep track of events? What if time is the actual substance, the thing that everything comes from? That's the core idea behind temporal strand theory. In this model, time isn't passive, it flows. It stretches, it compresses, it can carry structure, it can interfere with itself, and it can collapse. And everything we see in physics, particles, mass, gravity, even space itself, comes from how time behaves. Particles in this view aren't tiny objects flying through space. They ride along one-dimensional temporal strands, and when a particle has mass, it compresses the flow of time around it. Like a boulder placed in a river, that compression causes the temporal current to slow down in that region. And just like water, drifting towards slower-moving currents, nearby particles naturally drift toward that slower flow. That's what we experience as gravity. Not a force pulling things in, but a gentle shift toward areas where time is compressed and flowing more slowly. Think of time as a river, always moving. Drop a rock in the river and the water slows around it. Leaves and debris floating nearby get pulled toward the slower current, not because they're being yanked in, but because the flow around the rock is weaker. That drift, that's gravity. And the rock, that's mass, compressing time. This theory isn't just a metaphor. It leads to real predictions, things we can test in a lab and in space. If time is structured and physical, it should leave signatures we can measure. That's what makes this so exciting to me. It's not just philosophy, it's physics. So that's the starting point of temporal strand theory. Not space, not force, time itself. Active, structured, and at the root of everything. Now, if you're wondering how this all ties together, here's where it gets interesting. In temporal strand theory, I treat time as not just a flow, but a structured medium. I picture it as made of one-dimensional strands, like threads in woven fabric, except these threads aren't in space. They're what gives rise to space. These temporal strands carry the flow of time itself, and it's the shape, density, and interaction of these strands that creates what we experience as particles, fields, and gravity. Each strand flows forward, but the flow can be compressed, stretched, or knotted. Where time is flowing normally, we see the speed of light. That's because the speed of light isn't really about how fast light moves through space. It's the fastest rate at which time itself can flow along an uncompressed strand. So when we say nothing can move faster than light, what we're really saying is that nothing can move faster than time flows when it's fully relaxed. Now mass, as I said earlier, slows that flow. A massive object compresses the strands around it, and that makes time tick more slowly nearby. Light passing through that region doesn't change its intrinsic speed, but its path bends because it's tracing the geometry of time. That's what we interpret as curved space in general relativity. But in my model, it's just bent time. And here's the key. You don't need to assume space is curved. If time is compressed in certain areas, everything behaves as if time were curved. You still get gravitational lensing, You still get orbital mechanics. But instead of warping space to explain those behaviors, you're just watching how things move along a flow of time that varies depending on the surrounding mass. This flips a lot of assumptions upside down. Instead of asking how space bends or how mass affects spacetime, I ask, how does mass alter the flow of time? And if you model time as a real physical medium, something with tension, direction, and compression, you start seeing all the same phenomenon, but with a new kind of simplicity underneath. So in a way, this theory doesn't discard relativity, it reframes it. It says, what if all that bending and stretching is happening in time, not space? So let's talk about the quantum side of things, because this is where temporal strand theory starts to pull gravity and quantum mechanics together. In traditional quantum mechanics, we're told that particles behave like waves until they're observed, and then the wave function collapses into a single outcome. But what actually collapses? What does that even mean physically? That's always been a murky part of quantum theory. In temporal strand theory, I propose something different, that what collapses isn't a wave function in abstract math, it's the structure of time itself. Let me explain. In this model, particles move along one-dimensional strands of time. As long as those strands stay coherent and aligned, the particle retains its quantum behavior, like the ability to interfere with itself or stay entangled with another particle. But once it interacts with something else, like a detector or another particle, everything shifts. These systems typically distort the temporal flow, either due to mass, structure, or decoherence. When a coherent strand enters that kind of environment, it loses its alignment, the structure of time breaks down, and that collapse is what we experience as measurement. But this isn't some mystical collapse of the wave function. What's really happening is a structural shift in the time medium itself. The strands fall out of superposition, out of their multiple potential paths, and settle in one dominant direction. That's what gives a particle its definite position, spin, or state. It's not magic, it's time arranging its flow. This same principle explains entanglement too. When two particles are entangled, their temporal strands are synchronized, even across what we perceive as distance. They're sharing structure, not information. So when one collapses, the other structure shifts too, because they are already part of the same temporal configuration. No spooky action required, just 2 points along a single stretched strand of time. Decoherence, interference, superposition, all of these emerge from how time flows, overlaps, stays aligned, or falls out of sync. We don't need to invoke mystery. We just need to give time the physical agency it's been missing. What this means is quantum behavior isn't floating on top of spacetime. It's a natural outcome of how time itself behaves. Once we treat time as the real substance, not space, quantum effects start looking a lot more grounded and a lot less weird. Now let's talk about how this plays out at larger scales, because gravity, redshift, and black holes all follow naturally from this same structure. In our everyday world, gravity looks like a force. Things fall toward Earth, planets orbit stars, and galaxies curve around dark masses we can't see. But if we start from time, not space, we get a different picture. Gravity becomes a flow phenomenon. Whenever temporal strands get compressed, time slows down. That creates a kind of temporal gradient, a current, and everything drifts towards slower regions. You can think of it like water in a river. If there's a boulder in the stream, the flow wraps around it. The water is denser there, moving slower. The same thing happens in time. Mass compresses the flow, slows it down, and everything else is drawn toward that slow zone. That's not attraction. That's not curvature. It's flow dynamics in a temporally active medium. This model also reinterprets gravitational redshift. When a photon climbs out of a compressed region, a place where time is flowing slowly, it stretches, not because energy is being lost, but because the temporal flow is changing. The wavelength elongates to match the faster stream outside. The photon isn't losing anything. It's just staying in tune with the fabric of time around it. So what we call redshift, or time dilation, or even gravitational potential, all of it, it's just time, flowing differently depending on what's around. Now let's go deeper into black holes. In general relativity, black holes are regions where space-time is curved so extremely that not even light can escape. They're treated as singularities, points of infinite density where the known laws of physics break down. But in my framework, I see black holes differently, not as spatial holes or singularities, but as temporal knots, places where the strands of time itself have been compressed so tightly they essentially dislocate from the surrounding temporal flow. Imagine a river. In most places, the current moves slowly, guiding everything downstream. But now picture a massive obstruction, a whirlpool forming, where the current gets twisted, spinning tighter and tighter until that region becomes isolated. That's what a black hole is in the temporal strand model. Not a tear in space, but a region where time folds so tightly on itself that it becomes almost inaccessible from the outside. Not gone, just cut off, like a knot that time can't untangle. And that shift changes everything. It redefines the event horizon, not as a spatial boundary, but as a temporal threshold. Once something crosses into that tightly knotted region, it's no longer just falling into space. It's entering a zone where time itself is almost standing still. From our perspective, it disappears. But from the inside, something very different might be happening. This is where things get interesting. One of the great unsolved questions in modern physics is the black hole information paradox. According to quantum theory, information can't be destroyed. But if something falls into a black hole and disappears forever, where does the information go? Traditional models can't answer that without invoking speculative solutions like holography or firewalls. But if black holes are temporal in nature, if they're made of dislocated time, then the information isn't lost spatially. It's just displaced temporally, still encoded in the structure of the strands, just no longer accessible from our frame of time. In other words, instead of asking where the information goes, we should be asking when it goes. From the outside, we see loss, but from the inside, from the compressed, slowed down frame, the story is still playing out, maybe even reversing. And that opens the door to rethinking not just black holes, but cosmology, entropy, and the flow of time itself. Now let's talk about one of the most important implications of this theory, the speed of light. In our traditional physics models, we treat light as something that travels through space at a constant speed, 299,792,458 meters per second. That number is sacred, immutable. It's the foundation of special relativity, the barrier no particle with mass can ever cross. But in the temporal strand framework, I look at it differently. The speed of light isn't just about how fast photons move through space. In fact, in this model, photons don't move through space at all. They travel along uncompressed strands of time. What we think of as c, the speed limit of the universe, is actually the maximum rate at which time itself can flow along those strands. Let me say that again. The speed of light is the speed of time in its purest uncompressed form. That means when we measure the speed of light, what we're really measuring is how quickly information can propagate through unbent, unstressed time. It's not about photons racing through empty space. It's about temporal geometry, time stretched out like a wire, and light riding it at full capacity. And here's the twist. When time gets compressed, it flows more slowly. That's why clocks near massive bodies run slower. That's why GPS satellites have to correct for both gravity and speed. Not because time is being distorted by space, but because space is just a projection of time's underlying structure. In areas of high mass, the strands of time get tighter, denser, like the narrowing of a river. And in those regions, light still travels at c, but that c is relative to local time flow, not some universal canvas. This has real implications. It means we may be misinterpreting redshift, gravitational lensing, and even time dilation. If we think in terms of spatial curvature, we get a certain picture. But if we look at it through a lens of compressed time flow, the whole thing starts to make a different kind of sense. We stop thinking of light as moving through a distorted space and start seeing it as tracing the shape of time itself. That's a profound shift, and one that might help us bridge the gap between quantum mechanics and gravity. And that changes everything. If light isn't crossing space but writing time, then maybe all the strange phenomena we see in quantum physics aren't strange at all. They're just symptoms of how time really works. In part 2, we'll go deeper into entanglement, interference, and black holes, and I'll show you how the time-based framework rewrites the rules of quantum mechanics and gravity alike. Let's keep going.